All right, let's talk about one of my favorite ideas in all of computer science. It's an algorithm that's so elegant, so powerful, it can take a problem that seems impossibly huge and just shrink it down to nothing in the blink of an eye.
So I want you to picture this, a massive sorted list. And when I say massive, I mean it. We're talking 1 billion records. That's 1,000 million. No typos here.
And here's the big question, right? Somewhere in that absolute ocean of data is the one thing you need to find. So how do you do it? I mean, where would you even start with a number that big?
Well, there is the obvious kind of brute force way. You could just start at the very first record, number 1, and then check number 2, then 3, and so on. We call this a linear search. Think of it like looking for the word zebra in a dictionary by starting on page 1 with the A's. Yeah, you'll get there eventually, but it's not exactly clever, is it?
And this is where that simple approach just completely falls apart. With our billion record list, if the item you're looking for happens to be the very last one, you'd have to do 1 billion checks to find it. In the real world, that's just not going to fly. That's completely useless. But what if there was a secret, a key insight? And there is. It's right here. If, and this is a huge if the data is already sorted, you can do something amazing. With every single guess you make, you can throw away half of the problem. And that, my friends, brings us to binary search. It is a beautiful algorithm that's built entirely on this idea of halving. You find what you're looking for by just cutting the search area in half over and over again. But you see that word in all caps, sorted? That is the one single non-negotiable rule. Okay, so talk is cheap. Let's actually see this thing in action. I'm going to walk you through it step by step. All right, here's our test case, a simple sorted list of 10 numbers. And our mission is to find the number 23. We start by setting up 2 little bookmarks, or pointers. We'll call them low, which starts at the very beginning, and high, which starts at the very end. Then we find the exact middle. In this case, the middle is at index 4, and the number sitting there is 16. So now we ask our first question. Is our middle number, 16, the number we're looking for? Nope. But, and this is the magic part, we know that 16 is less than 23. And because the list is sorted, we now know for a fact that 23 has to be somewhere to the right of where we are. And boom, just like that, with one simple check, we throw away the entire left half of the list. It's just gone. We don't need to look at it ever again. We've cut our problem in half. So we just move our low pointer up and find the new midpoint. Now we're looking at index 7, which has the number 45. Okay, round 2. Let's do it again. Is 45 our number? Nope. This time, 45 is greater than 23, so we know our target must be in that small section to the left of this new midpoint. So we chop off the right half and we move our high pointer. Look how small our search is now. It's just between index 5 and 6. We find the new midpoint, which lands right on index 5. And the value there, it's 23. And there it is, found it. We got our target at index 5. Now think about this for a second. It only took us 3 checks to find our number. A linear search, going one by one, would have taken 6 checks. So that incredible speed, that wasn't just a lucky guess. That efficiency is built right into the math of how this thing works. In computer science, we have a fancy name for it, logarithmic time complexity, or O of log n. And understanding this is the key to seeing why binary search is such a huge deal. Just think about it like this. Every single time we make a comparison, we cut the problem in half. If you start with n items, after one step, you have n divided by 2. After the next step, n divided by 4. So the real question is, how many times can you chop a number n in half before you get down to just 1? That number of chops, well, that's the logarithm. That's what we're measuring. So let's go back to our big, scary 1 billion record problem. Linear search, worst case, could take 1 billion comparisons. But binary search, its worst case is the log base 2 of 1 billion, which is about 30. 30! I mean, come on, from 1 billion down to 30. That's not an improvement, it is a complete, total game changer. And this is not just some neat academic trick either. This algorithm is the invisible engine behind tons of technology you probably use every single day. Any programmers watching will know this. There's a tool called Git Bisect that helps you find a bug. It basically does a binary search through your code's history. You tell it the bug is here or the bug isn't here yet, and it instantly cuts the number of suspects in half. It's also the core idea behind how databases can pull up your data in milliseconds. Even the autocomplete on your phone uses it to search a sorted dictionary of words as you're typing.
Now, really quick, when you go to actually code this thing, there are two popular ways to do it. The iterative way just uses a simple while loop. The recursive way has a function call itself on smaller and smaller pieces of the list. The main practical difference you need to know is about memory. The loop uses a tiny, constant amount of memory, while the recursive one uses a little bit more memory for every step it takes, which can matter in some edge cases.
So we've seen how it works, why it's so ridiculously fast, and where it shows up in the real world. But all of this power, all of it, depends on one single, unbreakable rule.
This is it. This is the golden rule. The array has to be sorted. Period. The whole logic of if this is too small, look right, or if this is too big, look left, completely falls apart otherwise. Without a sorted list, binary search is just gibberish. This is the key that unlocks its power.
And you know, that really leaves us with a final thought. Binary search is an amazing algorithm, for sure, but it's also kind of a powerful metaphor. It proves that sometimes the hardest part of solving a problem isn't the complex search itself, but just doing the prep work, just getting things organized. And it really makes you wonder, right? What other huge, impossible problems out there become almost trivial once you take the time to organize the data first?